Alright, so this is the first of 3 videos on matrix multiplication that we will go through for the material in section 4.3 of the textbook. Um, so for those of you who found section 4.2 to be a little bit abstract, you might be happy with this section of the book. Everything here is very concrete and computational. The only thing with matrix multiplication is that the process is a little bit counterintuitive, and it's something that you might need a bit of time to get used to, but as with most of the computational things in this class, um, with you know, with a bit of practice, matrix multiplication becomes pretty routine. It becomes something you can do without having to think too hard about it. So let's, to introduce the idea, we're going to warm up with a, well, okay, I put practical in quotes because I don't know. I have no idea if this example has any connection to reality or not. It probably doesn't. But we could imagine some sort of scenario where we've got a farm that raises livestock. We've got cows and pigs in this case, and then each one is provided with some grain feed. I've gone with corn and barley in this case. So whether or not these are appropriate feeds for these animals, ethics of, grain-fed versus grass-fed cows, we're not going to get into any of those sort of details here. We just want to solve one particular problem, which is if these feed crops are grown using some sort of chemical fertilizers, and there's a certain amount of chemical that is absorbed by each crop when these fertilizers are applied, how much of these chemicals are passed along to each animal? So how do we figure that out, right? So the first matrix that we have here, the first matrix keeps track of how much of each chemical is absorbed by each type of feed, right? So the first matrix establishes this relationship between the chemicals and the feed. We can think of this, if you like, you can think of this matrix as establishing some sort of function that assigns to each type of chemical, assigns the amount of that chemical present in the feed. The second matrix, if you like, looks like some sort of, again, what this one is doing, if we want to think of it as a function, this one is a function which for each type of feed assigns to that feed the amount of feed that is eaten by each animal, right? So corn is assigned to the number 27 for cows. Cows eat 27 kilograms of corn, and 15 for pigs. Pigs are eating 15 kilograms of corn. Again, these numbers might be completely unreasonable. Maybe 15 kilos is probably way more than a pig could eat in a week. But yeah, who knows? Maybe it's accurate. I'm not sure. The numbers are completely made up. The problem, however, is a reasonable one. How much of each chemical is consumed by these animals? So think about doing, let's say we want to know how much of chemical 1 is consumed by the cow. Well, how do we figure this out? We say, okay, so the cow eats 27 kilograms of corn. And since we know how much corn the cow eats and we know how much chemical is in the corn, we can multiply those. So 27 kilograms of corn times 1 milligram per kilo of the first chemical. That tells us how much the cow is consuming by eating the corn, but we also have to add on the amount that is consumed from eating the barley. So there's an additional 15 kilograms of barley, and we multiply by, so the first matrix says that there are 2 milligrams of the second chemical for every kilo of barley. And so what do we get? We get 27 times 1 plus 15 times 2. And so we get 57. 57. Make sure I add correctly. Let's fix that up. 30 plus 27 gives me 57 milligrams of the first chemical. One of the things you may want to notice here is that you get something that looks suspiciously like a dot product, right? And you could do this again for, let's say I want to do it for, maybe I want to do the pig. and I want to do maybe chemical, let's say 2, right? So what would I do for, if I wanted to know how much of chemical 2 is consumed by the pig? Well, I would do my 15 kilograms of corn coming from here. I would multiply by the amount of chemical 2 that's in each kilogram of corn, which is a 2. And then I would do so the pig is eating 5 kilograms of barley, and in each kilogram of barley there is 1 milligram of chemical 2. So I would do 5 times 1, and so I would get 30 plus 5, I would get 35 milligrams. And again, we get this sort of dot product, right? So notice that what we're doing here is we're basically taking a row from the first matrix, and we can think of this as a row vector. It's a two-dimensional row vector. We're taking a column from the second matrix, which is also a two-dimensional vector, in this case a column vector, and we're combining them in sort of a dot product operation. We're putting the two together and we get out a number, right? And so we can do this for each row and for each column. And so what we're trying to figure out overall is, we want to figure out, okay, we have chemical 1, chemical 2, chemical 3, we have our cows, we've got our pigs, and we want to end up with, knowing how much of chemical 1 is consumed by a cow. So we worked that out. That was 57, right? And notice that that's the entry in the first row and first column here, and the way we obtain it is we take the first row from the matrix on the left and we multiply by the first column of the matrix on the right. If I want to know how much of chemical 2 is consumed by the cow, well then I should be doing, so chemical 2, this is going to be that's row 2, column 1, right? Second row of this matrix, first column of that matrix, how much of chemical 2 is consumed by the cow. So I go over to the second row for this matrix to get chemical 2, first column for this matrix to get the cows, and I'm going to be doing 27 times 2 plus 15 times 1. I'm going to get to 69 milligrams there. And then if I wanted to know what goes in the third row, first column here, how much of chemical 3 is consumed by the cow, I'm going to go to the third row here, and I'm still in the first column here. So 3 times 27 plus 2 times 15, that's going to give me 111. Then I do the same thing for the pigs, right? So I go back now, the pigs are in the second column, so I want to do first row times the second column to give me the amount of chemical 1 that the pigs consume. So I get 1 times 15 plus 2 times 5. I get a 25. Row 2, column 2, that's the amount of chemical 2 consumed by the pig. We did that one already. And then the last one would be chemical 3. If I take the third row, that's the chemical 3 times the second column. That should go in the third row, second column here. So 3 times 15 plus 2 times 5, and I get 55 there, right? So we can work out those numbers. That, in a nutshell, is how matrix multiplication is going to work. We'll see that is basically a specific case of the general procedure. Okay, so we saw that the kind of essential ingredient here, that we do, for each row and for each column is we take a row from the left, we take a column from the right, and we multiply them together. So those are sort of the building blocks, right? So the building blocks are this row times column procedure. And doing a row times a column, it is really just a dot product, right? So it's going to be A1 times B1, right? First entry from R times the first entry from C plus A2 times B2. I multiply the second entries together and so on down to AN times Bn. So I form each of those products and then I add them all up. It's just like doing the dot product, right? Once I've added everything up here, I get some sort of number that comes out, right? So for example, let's say my row looks like 3 minus 1, 4. Now, so if my column was, something like, 2, 1, okay, Well, I can't do anything with that because, if I wanted to do row times column, I can do 3 times 2, I can do minus 1 times 1, but then the four doesn't have a friend over here in the column, right? Because there's only two numbers in the column, there's 3 in the row. Each entry in the row needs to have a buddy over here in the column that they pair up with, and so my column is the wrong size, so this wouldn't make sense. The way I get these things to work is I make sure that they're the right size. So maybe I do 2, 1, and maybe minus 1. Okay, then I can do R times C. R times C is going to be 3 times 2 plus minus 1 times 1 plus 4 times minus 1. So I get 6 minus 1 minus 4. I get 1 for that product. Okay. So the next step is to basically extend this a little bit and consider the case where we have several rows. Of course, eventually we'll be having sort of many rows from the left and many columns from the right, but we'll just to kind of warm up, we'll go from one row on the left to having several rows on the left. So what we'll do here is we'll say, okay, I've got a matrix A, it's an m by n matrix, and I want to think of this m by n matrix as a collection of rows. So I have A11, A12, down to A1n, A21, 22, over to A2n, okay, down to AM1, AM2, and across to AMN. Okay, so there's my m by n matrix, and I want to kind of divide things up like this. I want to think of this as being like row 1, here is row 2, and so on down to the last row, row m. Okay, and what's important here is not the number of rows. The only thing that the number of rows is going to affect is basically the size of the output, right? So m is going to be the number of entries in the final product. When I do A times X, I'm going to get an m by 1 matrix. So the number of rows is going to determine the size of A times X. But as far as whether I can even carry out the product in the first place, what matters is that if each row of A has n entries, A11, A12 down to A1n, right, there are n entries there are n columns, then X also needs to have n entries, right? So X here, X looks like X1, X2, down to Xn. Okay. So I can form this product A times X because I can do A11, right? I can do A11 times X1, I can do A12 times X2, and so on down to A1n times Xn. I can form that product. So basically I can form row 1 times X. I can do row 1 times X, that's defined. I can do row 2 times X, that's defined all the way down. And so what I do is I say, okay, A times X, I'm going to think of that as row 1, row 2, down to row m times x, and the result is going to be a m by 1 column vector where the first entry is the dot product of row 1 with x, the second entry is the dot product of row 2 with x, and so on down to the last entry, which is the dot product of the last row times x. So just to give you a quick example, if A looks like, maybe A looks like, let's say 3, minus 1, 2, 4, minus 1, 5, and X looks like, let's say 2, 3. Right? So A times X is going to be what? So I do the first row, so we divide things up. So row 1, row 2, row 3. So the first row times X, I do 3 times 2 plus minus 1 times 3. That's row 1 times X. Now we do row 2 times X. 2 times 2 plus 4 times 3. Then I do row 3 times X. Minus 1 times 2 plus 5 times 3. Okay. and I carry out each of those products. 6 minus 3 gives me 3. 8 plus 12 gives me 20. Minus 2 plus 15 gives me 13. Okay, and I get that product. All right. But there's actually another way that you can think about computing this product. The other way that you can do it is you can take your matrix A, A11, A12, all the way down to A1n, 21, 22, over to A2n, and all the way down to A M1, M2, Mn. So there's A, here's my X, and X1, X2, down to Xn. And so the other way to do it is to say, well, you know what, I could divide A up into columns, column 1, column 2, down to column n. And I could basically say, you know what, for each column in A, I have a corresponding number in X, right? So I kind of column 1 I can match with X1, column 2 I can match with X2, all the way down to column n times Xn. And so I could also make this definition. I could basically think of this as like a dot product, except that, you know, I'm doing x1 c1 x2 c2 down to xn cn, but these c's are not numbers anymore, they're vectors. And so when I form this, right, a times x, what I'm going to do is I'm going to say a times x should be x1 times c1 plus x2 times c2 down to xn times Cn, right? And so what have I got? Well, what I've just done is I formed a linear combination. Right? So the other way of doing a matrix times a column is you can think of it as forming a linear combination of the columns in the original matrix. So let's check that this actually gives us the same result. You can work it out for yourself if you want. I think we'll skip, because we don't want this video to get too long, we'll skip working out the general details, but you can kind of see what will happen. All the numbers in column 1 will get multiplied by x1, all the numbers in column 2 get multiplied by x2, and so on. And when you add everything up, you do get the same thing that you got before. You'll still get all these numbers times x1, all these numbers times x2, and so on. And to see that that is indeed what you get, let's try this example that we have here. So if we take the same matrix, 3, minus 1, 2, 4, minus 1, 5. Let me just double check to make sure that that's what I had. Okay. X being the column 2, 3. So this this recipe says that to do A times X, I should do first entry in X, which is a 2, times the first column in A, 3, 2 minus 1, plus the second entry in X times the second entry in A, minus 1, 4, 5. So this gives me 6, 4 minus 2, minus 3, 12, 15, and when I combine those I get 3, I get 3, 16, and 13. Okay, and that's not the same. It's not the same because I messed this one up. 2 times 2 is 4, guys, not 8. 4 plus, yeah, there we go. I'm doing these videos before I finish my coffee. 4 plus 12 gives me 16. So they do come out to give me the same result, whichever way we do it. Good. We'd be worried otherwise. Now the other thing you could think about is you could think about doing a row times a matrix. This is something that you'll sort of see less often. But if you want to, you can think about doing a row times a matrix. So A1, A2, down to AN, right? And we know how to do a row times a single column. So if we think of B as consisting of many columns, B1, B2, down to BP, right? So if I think of this, so this is my This is my R, right? Then I can do that row times the first column, so row times B1, and then row times B2, and so on down to row times BP, right? So if I have one row on the left and many columns on the right, I just do row times column for each one of the columns, right? Whereas when we were doing a matrix times a column, we said, well, we have many rows on the left, one column on the right, we do each row times the column. So of course you can see where you go from here. If you want to do general matrix multiplication, we'll consider that in the next video. If I have many rows on the left times many columns on the right, then I'm just going to do each row times each column. I'm going to do row times, so that's kind of the general picture. So the general case would be you think of your matrix on the left as a collection of rows, so row 1, row 2, and so on. You think of your matrix on the right as a collection of columns, B1 down to BP. And as long as the number of entries in each row matches the number of entries in each column, then you can do row 1 times B1. You can do row 1 times B2, and so on down to row 1 times BP, and then row 2 times B1, and so on. And that's going to be how we do matrix multiplication in general, and we'll explore that in the next video.